he meanders a bit, but he knows a lot of good stories.
Very cool.
But you can hear like all the sounds that travel through these.
Does this thing just, do they hand it to us on? Do you know?
Yeah,
It's on. Okay.
you know how to turn it on and off.
No,
You want to learn it.
not really. Okay. You got Zoom?
Yeah.
Okay.
No, Jack.
If you want to handle Zoom, I can switch.
I'll just go flag you down when we have it.
Cool. Moment of anticipation.
Mm-hmm.
Officially. Yes, we have all kinds of slides for the
Yeah.
which I was going to say.
Camera 2.
I've become, you know. Yeah, but no, it's bad guy, just like that. How you fill out the form, what the form means, I don't know. What dates mean?
Now we have a share in Zoom, and then did you guys play in Google Compact?
Evil cop.
The only way things actually get done.
Bloody fines.
Wow, what would that look like?
I don't know exactly, like you turned in this thing late, that's $10, or you did this thing, that's a big,
Are you
giving away my
late?
money.
See, 'cause
Man,
I
I'd
don't
be
know how
bankrupt,
it
I'll be
money out of
bankrupt in about
it.
6 months. I think I've turned in one thing on time in like the entire last 2 years.
Jim, it works the other way too. If you give me this, I'll give you that thing.
Hey, bud.
Yeah, there you go. Payolas, yes. Payola.
Payola.
To the graduate.
Definitely work that way.
I keep looking at my watch, but it died.
You were.
It died like
Had
like
one just
15
moments
minutes
ago.
Isn't that how technology works? You just keep looking at it long enough.
Yeah, it'll eventually die.
Reanimate.
Make sure I didn't leave my phone in the other classroom. Is Sonia on?
I did send
Do they have theme?
nasty note to
Well,
classroom
there's,
services.
they can't.
About
They don't need to.
which room?
I'm originally thinking about
Holding
that.
244
Core.
and like Crestron touch my
Hey,
hand.
Oh.
Beatty and Taylor, can you guys just do like a quick 1-2 microphone check?
1, 2, check, check. Microphone check. 1, 2, 1, 2.
1, 2, check, check, check. Right.
If you get a message from
Okay. I usually don't hear. Sonia on?
STS staff
Oh.
never seems like
Oh.
a little uptight about it.
Non-working technology, but
I apologize,
She
I
really-
launched in the
Right.
whole thing. But they was telling me the firmware.
Oh, she's joining.
there she is. Okay. And it's time, so I'll start going now. Oh, okay. Hi, everybody. Welcome to the STS seminar, where we're going to have Taylor Loy speak here in a moment. I'm Lee Vinsel. I'm one of the co-organizers of the seminar with Fernanda Rosa. I am going to hand off introduction duties to my colleague Sonia Schmidt, who abandoned the STS seminar organizing crew this semester. So I don't know how I feel about her doing introductions, but she's going to introduce Taylor for us very gratefully. And I just want to take a moment to thank two groups. I want to thank the Athenaeum for doing all the hard work to create this great stream for us. And I'm not going to be here next week, so I also wanted to take a moment to thank Oliver Shuey. Yeah, exactly. Thank you. Yeah, Oliver has done such an incredible job this year and really supported us in all kinds of ways. This thing just would not have happened without Oliver. So I want to take a moment and say that out loud because I won't be here next week to put him on the spot and embarrass him in this way. And with that, I would like, Mandy, if you could hand it over to Sonia, who's going to introduce our wonderful speaker, Taylor Loy, for us now.
Hello, everyone. Can you hear me?
Try a little louder, but if not you, more volume.
I'm having trouble hearing you guys, but
Yes, Sonia, we can hear you.
But now you're
in the STS PhD program. And so he got his master's degree in STS from Virginia Tech. He also got a master's in English literature at the same time in 2008. And then he left Virginia Tech for a significant period of time, during which he went to work for the nuclear industry. And he working for Browns Ferry and working as an operator instructor. So he actually trained nuclear reactor operators for about 6 years before he returned to you will learn more about in a moment. I just wanted to, it says, it's frozen. Yes, I'm having trouble with my internet. I am at work in the conference room at Virginia Tech. So.
Not to put too fine a point on it, yeah. Well, thank you, Sonia. We'll make sure Taylor gets your written introduction so he sees all the wonderful and glowing things you said about how great he is, which I agree with wholeheartedly. And with that, I'm going to hand it over to our friend Taylor Loy.
Thank you so much. Thank you, Lee. Thank you, Sonia. I'm really glad to be here. And today I'm going to talk to you about my dissertation on tritium, titled, can we bring up the slideshow here? Titled Tritium Matters, Constructing Nuclearity and Navigating Ambivalence of a Unique Material. So before I dive into it, an overview of what I'm going to talk about, a little bit of the scope and structure, some idea of the chapters, how I laid it out, and so what, like why is this important? So first of all, the scope and structure, I'm looking at tritium as a material from its discovery, 1930s, till today. So it's kind of a broad survey. I got a lot of ground to cover, so I'll try to be efficient. I'm covering 5 topical chapters in my dissertation. First one will just be an introduction to my theory elements that I'm going to be using. Chapter 2 is a broader look across this history of tritium from when it was born nuclear, looking at different phases of its development. And then the next 3 chapters, I look at implications for these phases, these characteristics that I'll tell you about shortly in a couple different domains. One is non-proliferation policy. Second is as a tritium as a pollutant, as a radioactive waste material, as a byproduct material. And finally, in the final chapter, I talk about the potential for tritium to fuel fusion energy, a fusion energy industry, which doesn't exist but may one day. So the bottom line up front, my core argument that I argue in this dissertation, that expert conceptions of tritium have experienced interdependent and overlapping phases. Each phase is characterized by dominant nuclearity, which I'll define, that directly and indirectly affects material conditions, elite decision-making, and radiological impacts on the environment and human health. Sort of secondarily, the future implications of my work is that rather than allowing fusion energy proponents, who are talking about this a lot now, to dictate this next phase of tritium's nuclearity, its development, efforts should be made to assess and synthesize the salient aspects of this unique material to provide a more holistic accounting of its risks, benefits, and trade-offs. You all are dying to know what tritium is. Those who don't, listen up. So what and why is this important? So tritium is a radioactive isotope of hydrogen. It has 2 neutrons and 1 proton in a nucleus. It's one of 3 hydrogen isotopes. It's the only radioactive one. It has about a 12-year half-life. That means about 5% will decay in a given year, and 12 years you'll have half as much as you had when you started. It does exist naturally, which they didn't know for several years after its discovery in the lab, because it's so diffused in the environment. It is generated by cosmic rays in the upper atmosphere, and about 3.5 kilograms, there's various estimates, are distributed across the entire planet. So it's there, it's just very diffuse. Some experts have said that you cannot take a sample of surface water on the planet without having some tritium. There's an atom at least. It's everywhere because it functions just like other hydrogen isotopes. But we can't really extract it from the environment because it's so diffuse. So synthetic production is required if we want to use it for human means, human ends. And it's got several ends and means. One of those is in nuclear weapons. So it's a dual-use material. It was, and so it has sort of its first major use was in the hydrogen bomb, which I'll talk about. But it also has peaceful uses that are more innocuous. Radioluminescent applications, exit signs, watch dials, things like that. It's a very kind of ordinary material that's not particularly dangerous in extremely diffuse environments. So it's very useful for lighting and things, but also potentially for producing power through fusion energy. In order to produce tritium requires a large industrial footprint, so this is not something that can be easily done without substantial investment, capital, and infrastructure. And for the uses in nuclear weapons and for fusion fuel and several applications, there's no really alternatives right now that are viable. So it's the best material for several of these applications that we have. And by best, it helps make atom bombs explode a lot more violently than if we just left them to fission alone. This is a typical warhead. So, and most modern nuclear warheads incorporate some plutonium, some high-enriched uranium, and tritium. This allows for small, good weight to kiloton ratios. So you have smaller warheads, bigger booms. One NNSA field office manager recently said, without tritium, there wouldn't be a nuclear stockpile. It decays, we have to replenish it. So this is an ongoing issue for the nuclear weapons complex. What does it mean to decay? Quickly, tritium undergoes beta minus decay. Basically, a neutron emits an electron, turns into a proton. This is a low energy electron. It can't penetrate your skin. Its only real danger to human health is if it's ingested. It decays into a stable element, helium-3, which is very useful and rare on its own. And so one use that helium-3 is used for is large portal monitors for detecting illicit nuclear material that has potential neutron emissions. It has a high cross-section of absorption to neutrons, which means if a neutron's there in its presence, it'll have a good likelihood of interacting and causing an effect that we can measure. So, real briefly, these are my theory kind of frameworks that I'm drawing from STS literature. Initially, I really thought there was some potential in Adriana Petrina's life exposed framework of biological citizenship in looking at, for instance, comparing it to the Fukushima Daiichi disaster in relation to tritium. But even as she says in her 2013 edition of the book, it doesn't map on really well to the Japanese condition, and I think there might be some applications in the future. But I kind of looked at that as a likely candidate. But primarily, I'm dealing with Edie Abraham's notions of nuclear ambivalence and Gabriel Hecht's nuclearity, which is in my title, and nuclear exceptionalism, which I will define. So Abraham's notion of nuclear ambivalence is an essential nuclear condition, highlighting the simultaneous presence of more than one meaning of nuclear practices. So it's not exactly dual use, it's also a sort of complex array of things that are superimposed on each other. Nuclear ambivalence recognizes that nuclear and non-nuclear technological infrastructures are interconnected and interdependent. You don't have this definite, isolated nuclear thing that's separate from all non-nuclear things, right? So this allows the fluidity in your understanding of what counts as nuclear and non-nuclear and how they can reinforce each other. Abraham uses this in looking at sort of geopolitics and kind of criticizing and talking about nations going nuclear. The idea of having the bomb or not is not a binary position. It's a very complex thing. It's not just a leader of a country deciding, hey, we've got some nuclear stuff, we've got this, we'll have a bomb. There's a lot of affordances and a lot of path dependencies that gets acknowledged in nuclear ambivalence. And also provides a space for this multiplicity of technological affordances and policy-making processes, which I alluded to. Key term that I'm looking at that I draw from is Gabriel Hecht's term that she coins in Being Nuclear text, where she looks at uranium mining in the Africans. And so in this, the process by which materials and activities become designated as nuclear, right? This is not simply reducible to a material property like radioactivity. It's a diffuse parameter that encompasses materials, environments, work practices, workers themselves, geography, geology, governance, degrees of radiological risk. A whole slew of things kind of get packaged in how nuclearity is enacted for a given site, a given material, a given activity. Hecht clarifies this in her text, saying radiation is a physical phenomenon and that exists independently of how it's detected or politicized. I mean, just like tritium and its effects. Nuclearity, on the other hand, is a technopolitical phenomenon that emerges from political and cultural configurations of technical and scientific things, from the social relations where knowledge is produced. And lastly here, nuclear exceptionalism is the systematic insistence that possessing the designation of nuclear signifies an essential nuclear difference in a person, place, thing, or process, right? And we've already seen from the nuclear ambivalence that this is a bit of a, nuclear exceptionalism is a bit of a red herring because there's never any pure nuclear thing that's separate from anything else. So by assigning some sort of special nuclear exceptionalism to a technology or an infrastructure, misses things, right? It causes you to occlude some of the reality there. So for chapter 2, this is how I've broken out and separated these phases of nuclearity. So these phases, interdependent phases of nuclearity that have developed over time, a typology that I developed looking at surveying the history of tritium. So I identified in sort of the early Manhattan Project, bomb days, there was work on the super bomb that famously Edward Teller was a big proponent of. And I identified about 1942 to 1960 was this range, and this is a fuzzy boundary, right? These are overlapping and independent, and it has a certain dominance during this time. And so I'll describe this supernuclearity in relation to the superbomb. After that, it quickly kind of gets supplanted with special nuclearity, which is more familiar because to folks that are familiar with special nuclear material, S and M, like uranium and plutonium used to make bombs. Those are the things that are highly regulated and they're big in policy and they're talked about and they have significant quantities. And so tritium kind of goes into that sort of mode of being and the sort of nuclearity that I described. And that's about 1955 to 1990. It's kind of a dominant thing. Cold War, it's part of this sort of the routineness of the stockpile production. After that, there is kind of developing this notion of this byproduct nuclearity, which is currently the dominant nuclearity that I argue. But it's been in the works for quite some time. And this is nuclear waste, civilian production, and even commercial use cases. It's not simply just like byproducts, it's even when it's sort of used in kind of innocuous ways. It's defined that way. And for nuclear exceptionalism, I break this down into two typologies, and you kind of see this operate in different domains. So military exceptionalism has this absolute secrecy and this national defense justification. It's sacrosanct, right? Nuclear weapons are kind of treated that way in a lot of different contexts. But in nuclear matters, there's also this extension of peaceful exceptionalism, where you're seeing that more and more now in the context of climate change. It's a high density energy solution that uses a small amount of land. France is an example everyone will point to, the fastest decarbonization of any grid, national grid. There you go, nuclear power is exceptional. It's the way to save us from all this, right? And so sometimes it gets attributed this exceptional quality of energy production, that it's not, it can be true in part, but not true in total. All right, this is the hardest part of this. I'm going to do a quick survey of early nuclear weapons development and then talk about a couple examples. I could get lost in talking about any of these because they're so fascinating. All right, and so bear with me. So 1942 to 1949, you're going to have to fill in some blanks here because I can't do the history of nuclear bombs alongside this. Okay, so in 1942, Edward Teller and Enrico Fermi first kind of hatched this idea of a super bomb. This was well before the atomic bomb was proven and used. They were thinking about, let's make a bigger bomb from this material we just discovered. They quickly, some other Los Alamos scientists say, okay, hey, this will work better if we use deuterium and tritium together instead of just deuterium and deuterium to make a hydrogen fusion explosion. And from then on, in 1942, deuterium and tritium fusion became the mechanism that was going to be the ultimate bomb, the super bomb. So after the US used 2 nuclear weapons against Japan at Hiroshima and Nagasaki, just a couple days later, a very important report was released, the Smith report. I believe it's pronounced Smith, Smythe, was released, that covered the physics and basically is a sort of a proof of, hey, this is what we did and here's the stuff we can tell publicly. Soon thereafter, a Tolman report was on the Committee for Declassification, was done to basically determine what things could we tell, what things were secret. So soon thereafter, Edward Teller's wanting to make a super bomb really bad, so he's asking the new head of Los Alamos for 2 kilograms of tritium, which is an absurd amount, and I'll show you why. He doesn't get it, not in 1945. And they have a series of a conference on the super, and we have one of the first uses after that of the ENIAC, early programmable computer, which I didn't start this. And that estimated that one of the first things we used it for was estimating tritium for the super bomb, and there was around 300 to 600 grams for a single super bomb estimated. A couple years later, Enrico Fermi said maybe we could produce 10 grams of tritium a year. So, and it sort of led up to what I'll describe here, this 1947-48 tritium episode, when tritium was released from the military industry for research. 1950, Truman gave his super bomb speech, announcing to the world, we're going to build a hydrogen bomb, super bomb. I'll talk about that. And then soon thereafter, a couple other scientists, Ulam and Everett, realized that, hey, these estimates for tritium were very low, and it won't work. A super bomb won't work. So we have to try something else. And so they completely kind of threw the super bomb away and started going to different hydrogen weapon designs that use more modest amounts of tritium. And this led to the Teller-Ulam designs that sort of was the big innovation to create a thermonuclear bomb. There were a series of tests, and this isn't all of them that occur in this time. Notably, the U.S. Castle Bravo test was the largest U.S. test. It was a major radiological disaster, 15 megatons, way beyond what they expected. It used tritium and lithium deuteride, which is another sort of tritium-producing material. Importantly, and this I'll come back to this, the Soviet test in 1955, RDS-37, was one of the first true hydrogen bombs that was deliverable. This design is very innovative because it was a thermonuclear bomb that did not have tritium at the beginning. It only had lithium deuteride. That's important because it kind of flies in the face of the super bomb, supernuclearity that kind of clouds people's judgment. And then I'll talk briefly about the sort of the last vestiges of this sort of super mentality in 1960. So the Smith report, Smythe report, Henry DeWolf Smythe was chair of physics at Princeton, had a very granular, very basic understanding of, presented all this of how the physics of a bomb worked, and didn't reveal any sort of secret or dangerous information. But one of the things not mentioned in this entire text at all is the existence of tritium, which is a bit conspicuous because Smythe was a student of Lord Rutherford, the discoverer, the one who discovered tritium in 1934, and also Princeton Physics Lab was one of the first to isolate it from a sample of heavy water. So it was known, and Smythe knew it, and he intentionally did not include it in here, even its existence as a material, which is somewhat conspicuous. So this was before the Tolman report. So this is where things got, the definitions and the classification schemes got reified and became a little more fleshy. So look at a couple, we're going to just focus on tritium here because it's easy to get lost in this. But so in this committee, which includes Oppenheimer, Tolman, and several other notable scientists, they decided that, okay, tritium on these various axes, so we have basic chemistry, metallurgical, which doesn't apply to tritium as a gas, basic physics, nuclear physics, and technology. So tritium is class 1 in each of these, which means information recommended for immediate declassification. So, hey, we can talk about it, it's fine. Notably, this 4 caveat here under nuclear physics is the only recorded disagreement. So the footnote for this says, in the case of the DT cross-section, that's the likelihood of deuterium and tritium to react, to fuse, recommendation of class 1 was not unanimous. So they put class 1 in there, but there was disagreement about the DT cross-section. It doesn't go into it here, but it's pretty obvious. Robert Oppenheimer is one of, he kind of thought, hey, we can declassify this, hydrogen bomb's way off, this isn't going to give anybody an edge. And the third, class 3, was basically saying, was the information not recommended for declassification unless we have real reductions of threat of atomic warfare. So on this, the caveat here is that small-scale production methods are in class 2. So they keep this secret. The production is secret and still somewhat secret. They haven't declassified most of the production at Savannah River site. All right, So the two major sources of tritium in the U.S. Stockpile nuclear weapons arsenal came from Hanford site, and the vast majority of it came from Savannah River. So Savannah River plant has several SRS, Savannah Riverside, Savannah River National Lab, written several different ways. So in this, the blue here is Hanford, and so if you remember, in 1945, when Teller wanted 2 kilograms, and this is in kilograms, there really was zero production of tritium. It wasn't until like 1949 that Hanford produced 2.5 grams. So 2.5 grams of tritium got produced, and then the next year about 40 grams. And so we're entering the stage where Fermi was saying, hey, we can do about 10 grams a year. That quickly scaled up once they worked through some technical kinks. By 1955, purpose-built reactors at the Savannah River site began producing tremendous amounts of tritium. So these numbers come from two sources. The Hanford source is empirical data that was declassified in the 90s, and the Savannah River numbers were from a 1987 several volume set on called the Nuclear Weapons Data Book by Thomas Cochrane et al. And they estimated, based off publicly available information, like probably what they produced at Savannah Riverside, but it's never been declassified. So this is the only time I've seen these numbers kind of put together. And interestingly, between 63 and 67, here, the blue bars were part of a special co-product program, not co-production program, but co-product program, where they were trying to find better ways to make tritium for fusion, for peaceful use, right? And so these are experimental uses, and they were producing plutonium and tritium at the same time. So the co-product was plutonium and tritium, because they were anticipating needing plutonium for fuel as well. So that gives you a scale of where it's at and why it took so long for them to get the amounts of tritium they needed for these bombs. So this 1947-48 tritium episode, what this sums up to is there was arguments about releasing tritium or even talking about tritium to scientists and researchers because they didn't want to give anything away. And they were saying, wait, we're giving everything away. They'll see the big board. We're giving it all away because we're hiding it, right? So if we completely black out tritium, they'll know how important it is. So they go back and forth and decide, okay, we will release small amounts of tritium to these labs for academic research. And notably, they had a discussion here I have highlighted, but it's they decide not to have to ask the president to do this, but they talk about asking the president to release tritium, small amounts of tritium for academic research, which I think is pretty notable. Superbomb announcement from Truman, January 31st, 1950. It's part of my responsibility as Commander-in-Chief of the Armed Forces to see to it that our country is able to defend itself against any possible aggressor. Accordingly, he goes on to say, I've instructed the AEC to work on all forms of atomic weapons, including the so-called hydrogen or superbomb. The word had gotten out a little bit before that, but he stepped out, tried to get ahead of it, and tried to set the pace against the Soviet race to the hydrogen bomb. So this early phase characterized by the construction of tritium supernuclearity, as a material for a techno-scientific entity considered to be a crucial ingredient for unlocking the near limitless potential of nuclear weapons. So it's this unique thing that's more powerful than plutonium, more powerful than uranium. And there was a tension that was inherent in this between the public and restricted data that extends to this day on this because of this feeling about tritium, this construction, this nuclearity of tritium. So to give you a sense of the effects here, and this is going back to hey, the Soviets did a thermonuclear bomb without tritium. The Joint Committee on Atomic Energy Chair, Senator McMahon, meeting with General Bradley in February 1950, is distraught. He's like, I am constantly bedeviled by the thought that the Soviets, had done their hydrogen and atomic developments contemporaneously, and any idea that they aren't ahead of us, while I think the chances that they are not. But how do I know? We say, well, where would they get the tritium? And I believe that is the best assurance that we have got, that so far as we know, our intelligence, for instance, they haven't been in that particular business, but we don't know. So this tritium notion was really a kind of reassuring thing from the kind of policymaking perspective, that, hey, we're going to be ahead of them because we have this special ingredient that they don't. And so when they were able to keep up with us relatively quickly with their hydrogen bomb, it was somewhat of a surprise. And everyone kind of attributes that for many, many decades to Soviet espionage that you can ask me about questions if you want. The final kind of heyday of tritium's supernuclearity as being this sort of powerful thing, John Irwin, who's the Assistant Secretary of Defense for International Security Affairs in 1960 on the National Security Council, we have this declassified meeting where they're talking about fissile material cutoff. That's the agreeing to not produce uranium and plutonium for nuclear weapons. And Mr. Irwin spoke at length, and he says, hey, if we cut off fissile material and we keep producing tritium, since the H-bomb is considered worse than the A-bomb, we could be charged with holding on to the worst material. So even in 1960, there were some people saying that tritium was the worst thing there, and they were worried about sort of the global image as U.S. as being a moral leader in the sort of disarmament. All right. So that's moving on to special nuclear. How are we doing on time?
You've gone for about half an hour.
Perfect. So moving on to special nuclearity, the Atomic Energy Act of 1954 provides us a nice definition. Plutonium, uranium, enriched in the isotope 233 and the isotope 235, and other material which the Commission, pursuant to the provisions of Section 51, determines to be special nuclear material, but does not include source material. So the Section 51 provisions for designating material as special nuclear material. One, it must be capable of releasing substantial quantities of atomic energy. The designation must be in the interest of the common defense and security. And the President must expressly assent in writing that this material will be designated as special nuclear material. So I argue in this that the special nuclear material category is not a scientifically bound category, but a political one. It's often treated as if it's a scientifically bound category, as if it has these sort of kind of techno-scientific trappings, because it sounds that way. But the policy, this is a label we assign to these things, and it's open to addition. So there's no technical reason to exclude tritium from the special nuclear material category, only a lack of political will to do so. So it's never qualified, it's never been designated as a special nuclear material. However, that hasn't stopped many people, particularly in nuclear weapons complex and weapons, for calling it and thinking of it as a special nuclear material and referring it to without qualification, and in one instance with qualification. Here's just a quick example from a weapons symposium from 1969, proper unit cost of special nuclear materials, ore alloy, plutonium, and tritium. Ore alloy is is uranium, but it's short for Oak Ridge alloy. It's a particular alloy that was invented at Oak Ridge National Labs. And plutonium and tritium are just, they're side by side. They're all kind of equal partners in the nuclear weapon game. A really interesting example pops up later in 1980 in this long-range nuclear weapon planning analysis that was declassified later. So in the section on special nuclear materials, the special nuclear material used in nuclear weapons, plutonium, tritium, and highly enriched uranium, are expensive to produce and require long lead times to prepare for increased production. Their availability is a major determinant of a stockpile size and composition. And they have a note here. We use the term special nuclear material to include tritium, but it's not technically. So but they define basically what they say, special nuclear material are those materials that availability is a major determinant of stockpile size and composition, right? These materials. It's not anything else. It is these three materials. So in effect, in kind of informally and practically, it is functionally a special nuclear material that's on par with plutonium, highly enriched uranium and plutonium, weapons-grade plutonium, and is treated that way. Until near the end of near the end of the Cold War, just before the Soviet Union collapses, this idea keeps bringing. So this is a comment that was made on the tritium factor proposal, which is this idea that if we stop producing tritium and we just let tritium decay, then we'd have to disarm all our weapons as a function of decay. And these comments that were presented at this from the Deputy Assistant Secretary for Intelligence at DOE said, this is an old arms control idea, it's surfaced again, it's dangerously simplistic, it's very kind of alarming, it's very important to set the facts straight. So in this, they kind of demystify tritium and say, hey, it's not a special nuclear material, and here's why, and it's not qualified as such. And so it slowly becomes this anathema to talk about tritium in any sort of context of special nuclearity. And we see this play out in policy in a very dry, boring policy way that I will hopefully make very exciting. So material accountability and control, material accountancy and control is a DOE policy governed. So back in 1994, so from the 1980s until about 2011, tritium was treated as the same way as a Category 3 special nuclear material. And whatever that means, set that aside, but it was analogous to other special nuclear materials, and that slowly changed over the last 40 years. And so it began as tritium is, this is back in 1994, a nuclear material of strategic importance. Therefore, a graded safeguards program for tritium shall be established and follow equivalent to the following categorizations. So basically saying, hey, these are the different ways in which we will account for tritium in 1994. By 2011, the language changes to tritium becomes an other accountable nuclear material on a list of other things. And it says it's protected in a graded manner consistent with its strategic and monetary importance, and not just its strategic value alone. And then today, the most recent language, the version, drops the graded safeguards language and the graded manner, and it just sort of becomes another accountable material sort of generically aligned with others. So that, over that span of 40 years, you see that kind of play out in the policy. It goes from this special status to like a byproduct, just a separate thing to consider. And so we've come to byproduct nuclearity. So this becomes very dominant once the US decides to start producing tritium in a commercial light water reactor. A key document in that negotiation is this interagency review authored by Joan Rolfing that was presented to Congress in July '98. So this very explicitly says, hey, it's important to note that tritium is not a fissionable material capable of sustaining a nuclear reaction. Thus, it is not classified as a special nuclear material and is therefore not subject to prohibition in the Atomic Energy Act, blah, 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 as amended. So as we've just read, the definition of special nuclear material, you'll note that being a fissionable material capable of sustaining a nuclear reaction is not one of the necessary conditions, characteristics of a special nuclear material. It just has to be able to release a lot of nuclear energy, and tritium can do that. There's a little bit of some of this, the language becomes very targeted to separating tritium out from this special nuclear category, special nuclearity that it's kind of found its way into by practice. So by byproduct nuclearity, byproduct material as defined in the Code of Federal Regulations, it's any radioactive material except special nuclear material yielded in or made radioactive by exposure to radiation incident to the process of producing or using special nuclear material. So it's this extra thing, right? And it's not a thing in of itself, it's this byproduct. I'm going to quickly survey these last three things, sections that apply. Key text of non-proliferation policy is Martin Kalinowski's 2004 book on international tritium control. In this, he recommends that the global infrastructure create a unified system for tritium accounting, tritium control, using an integrated cutoff for special, for military tritium and a civilian integrated tritium control system. The genius part of this, and why this is such a compelling thing and why it actually hasn't been adopted or really considered, is that I believe it takes seriously both that special nuclearity and the byproduct nuclearity of tritium and puts them on kind of an even playing field, right? It's not trying to prioritize one over the other, and so it is a bit separate from sort of the dominant narrative around tritium. And so I endorse Kalinowski's recommendations, and I think that that this kind of exposes why his approach provides additional value that helps elucidate this holistic understanding of tritium. So in this preface to his book, Frank von Hippel kind of estimates, hey, if we have a fleet of fusion reactors to replace our fission reactors, there would be about 40 million grams of tritium, that's about 40,000 kilograms, in the supply chain, which is vastly beyond where we've ever been. And so how would that change things? We don't know. We need to think about it, right? So before this happens, we need to contend with this real possibility. I guess the last thing I'll touch on, because we're running out of time, this notion of tritium as a pollutant. So this is becoming more and more talked about, especially with the Fukushima Daiichi treated wastewater releases started last year. So tritium has a very kind of ambiguous effect on human health because it's really hard to measure and isolate these stochastic effects of cancer-causing agents and potentially dangerous things. And we know that it's relatively harmless in diffuse quantities, so it's like, where's the boundary there? And so Arjun Makhijani kind of looks at that and kind of brings up several underexplored domains of that have been brought forth for reproductive health, women's health, and the health of developing embryos, and their effect specifically of tritium, and not just this sort of kind of broad analysis of radiation deposited in flesh. It's like, what about these specific contexts? Tritium might be more dangerous. And so Makhijani kind of makes that case in his book that came out last year. And so the sources for this for tritium in the environment, the two main ones are nuclear weapons testing. This shows you a graph here. In 1963 was the peak when surface nuclear weapons testing stopped. And so the rainfall in around 1963 was equivalent to about 60% of what we would say the drinking water limit is for tritium in the U.S., which is 20,000 picocuries per liter. If you want to unpack that, we can talk about that. But and so, and that's been decaying and diminishing over time. In about 20 years, it'll almost entirely be gone from the atmosphere, as long as we don't start testing again, hopefully not. One example from one nuclear power plant that I study is Watts Bar, which produces tritium for nuclear weapons, incidentally. Intentionally, I mean, not incidentally. And so this is, I've compiled this information from available data from the NRC's website. And yeah, so to get a sense of scale, here in 2020, this highest point here, over 8,000 curies. A good way to translate this activity figure is 10,000 curies is about a gram of tritium. So over an entire span of a year, this site releases less than a gram into the environment, extremely diffuse, well below the drinking water limits and all those things. But these numbers are much higher than other sites in the US, and they've been higher since 2008, partly because they're producing tritium for nuclear weapons there. I'm happy to talk about that more. The final thing, fusion. Fusion proponents are really keen on separating out all fusion technology away from special nuclear material and from safeguards and all these dangerous things that they don't want you to think about. They want you to think about how safe and efficient fusion energy is. And so in this presentation, developing a regulatory framework that NRC hosted, all these participants joined in, and they each gave their takes on the future of fusion power. And so throughout, they would highlight, they emphasized that there was no special nuclear material on site. These are often bolded and highlighted and emphasized in several different ways. And that was seen as a major selling point. Our 5 takeaways. Here's my summary and end. 1, tritium was born nuclear and developed over the past 90 years through distinct phases: supernuclearity, special nuclearity, and byproduct. The super phase was resolved and superseded by the special phase in the 1950s and 1960s. Essential tensions between special and byproduct nuclearities remain. 3, while a nascent fusion energy industry is pushing for maintaining the byproduct nuclearity status quo, tritium's special role in nuclear weapons remains a point of neglect in nonproliferation and disarmament. Kalinowski leads the way, excellent model for solving this. And last, tritium's byproduct nuclearity will continue to be highly contested between anti-nuclear activists and nuclear energy proponents. The future trajectory of fission power and the scope of future fusion regulation will be significantly shaped by how tritium's risks are defined in this contested space. And all my references are publicly available. There's a lot of them. Thank you.
Beautiful. Thank you, Leo. So we're going to pass the mic around during the question phase, and if you have questions on Zoom, you can either put your question in the chat and we'll ask it, or you can hold up your hand and we'll have you come in. Taylor, I've never asked the first question, but I'm going to go ahead and ask you 2 questions this time. So for just the first one's easy. For the shady characters who are in the methods seminar this semester, they might watch this, and they're supposed to write about the methods the speakers use. Can you talk about just your research methods?
Absolutely. So I did a lot of extensive search in digital archives and databases because they're convenient, and there's a lot available that's been declassified and digitally available on nuclear weapons. And there's a lot of great resources available from the NRC's website on all the commercial power side of things. So a couple dozen different, just navigating the myriad archives that exist allowed me to accumulate over 500 relevant documents. I end up using a quite smaller subsection of that that are related to somehow informed my understanding. So that was a lot of the sort of primary material research. And this project began on a side project working with Sonia on tritium production at Watts Bar. And so in that we were doing interviews with experts, and I kind of snuck some of my tritium questions in with that. In that, I didn't sneak them in. That's part of the IRB. I did it properly. So
just to be clear.
Yes, and I also had a couple successful and unsuccessful FOIA requests for TVA. Yeah, and it was just accumulation of just tons and tons of information, and then use Zotero to organize it. And we could go through chronologically and really kind of make sense of it.
Beautiful, beautiful. And then the second question is, I heard a rumor that you think Langdon Winner's The Whale in the Reactor is not a great text on these kind of nuclear topics. And I was hoping that you might enlighten us a bit about that.
Sorry.
I'm glad. I'm glad you asked. No, I didn't want to. Yeah, so there is. I did consider and throw out several STS texts as being.
Winter was not in your list.
He wasn't on the list of ones I used.
Yeah.
So Langdon Winter is fantastic, and I really think that Well in the Reactor and Do Artifacts Have Politics very drew from this sense of like Lewis Mumford's like authoritarian democratic techniques, was very binary and very strict, and I think you see, and I think it's a fair criticism, because Langdon Winter in the 2020 second edition of his collected text, he has this sort of epilogue, and he talks about how Diablo Canyon nuclear power plant was closing, and the only people building nuclear power plants is authoritarian China. So he's right about everything.
Yeah.
And then 4 years later, everything Diablo Canyon is now open and will be open for another decade, and other people are building, and not just commies. I don't.
Yeah.
So, and I think that there's some other good texts in STS like Marone and Woodhouse look at the demise of nuclear energy, those lessons for democratic control of technology, and in that they kind of take a more like, hey, this is how it happened, but it's like in Clue, like maybe it happened this way, or maybe it could happen this way, and so they genuinely consider, hey, can these technologies be democratic, and how do we do that?
Yeah.
And Langdon Winter's like, they're intrinsically authoritarian. There's no way out of it. So, and that was just reductive, and I think it wasn't open to considering tritium as a fuel source and all these different things. It kind of just shut the discourse down.
Yep. Very nice. Yeah. Okay, we got a question there too. We'll go to Monami first, and then we'll go to.
Thank you, Taylor. That was really great, and I learned a lot, and it's really exciting to see it all laid out right there. You made a joke about co-production earlier, and I'm going to kind of ask you about that. In terms of, throughout this history, you see these different tensions between different loci of power. You have, what is revealed, what is not revealed at certain times, as how they relate to the categorization of tritium in different kinds of ways. And to me, this is almost sort of unpacking this agnotology, like the study of ignorance, of what you don't know, of secrecy. So I was wondering if you could talk a little bit about, or if you investigated in your dissertation, what kind of these social relationships of secrecy, of knowledge of what is known and not known, who gets to tell. So sort of the power question of it, what is this co-producing, this tritium categorization?
Excellent question, and I think I'll address it by sort of talking a little bit about the research methodology in a way. So the danger and the trouble and the difficulty in looking at nuclear weapons history, nuclear history, is that there's layers to it. And so if you go back and look at chunks of scholarship and like the history of this program, the history of this, and you read it at this point, and you read these a predominant scholarship on a good case, an excellent case is there was a bit of an expose in 1990 by Hirsch and I forgot the co-author. They had filed a FOIA request for a Hans Bethe memo from 1952 that looks at the hydrogen weapon program, and so that got released with some redactions, and mostly the redactions were quantities of tritium that would be required for some of these designs. And throughout that, they talk about they're worried about, and some of the people experts they interviewed that were still alive at that time in 1990, were worried about the Soviets learning their secrets from atmospheric testing from the bomb, like for the Castle Bravo, hey, they're going to know. If they sample the air from this, they're going to know what kind of nuclear processes were going on. And so they had this theory that was very it was very provocative, and it's like it was like, hey, this Klaus Fuchs, who was like a Soviet spy who revealed the secrets from 1946 in Los Alamos, he wasn't the one that broke the hydrogen thing. They were able to do it this way, and several years later, a few more things got released, and that turned out to not be true. It's like Soviets didn't really have a program at the time, atmospheric testing program at the time, due to now that we've learned from some Russian declassified documents and some Russian experts. So there are these layers that you see things that get revealed that kind of invert what is known and what is thought about, right? And there's something to that. There's more to answer that in Kalinowski's work, because Kalinowski has this, part of his reason why he thinks that tritium has been neglected for non-proliferation is because of secrecy, right? And I think that that's partially true, but I think it kind of misses, that there is a public understanding, a public suspicion, right? From the very moment that the superbomb was announced, like the next day, there was an expose like, oh, the Triton bomb, this is, and there was some people in the know that were like, suspected this, were putting stuff out, feelers out, and trying to guess what was going on. A lot of it was wildly off, but some things they had right, like the deuterium and tritium fusion was the principle. And that was widely known, and that was a lot of hand-wringing from the secrecy establishment. Like, how did they know, and how do we, keep that from becoming a danger to the program and things like that. And so, what did they suspect? And they were really worried a long time about who was saying what, who was allowed to say what, and the public might assume that so and so has some insider knowledge because they used to work for DOE or whatever. I don't think that was a really good question, and I'll have to think more about the implications of it, but hopefully I talked around it.
We'll go to a question on Zoom and then go to Matt. So you got one for me, Oliver? All right, here's one from Rich. Have you looked into tritium's use in commercial products? It's been historically used to illuminate exit signs, gun sights, watch dials, airport runway markers, amongst other things. Years ago, I saw a watch and sharper image catalog that said the dial was lit using tritium, found naturally in seawater. So have you looked at, have you gotten into?
It is found naturally in seawater. Just a bit. The commercial applications are somewhat innocuous and relatively small scale. So the major producer of illuminated timepieces is this company DB Microtech from Switzerland, I believe, and they process about 20 to 30 grams of tritium a year. So that's enough to supply. You need about 2 to 3 grams of tritium for a lot of conventional nuclear weapons designs, but they have very sophisticated tritium handling equipment, and that's how much they do. So 20 or 30 grams a year for timepieces on your wrist. But the nuclear weapons stuff, the U.S. is producing a couple kilograms a year to support our arsenal at Watts Bar.
Well, first I want to say, as one of those people who ran you out of town in 2008, we're thrilled to see you here at this moment. My question is about the strengths and limitations of nuclearity as a frame. And the whole time you were presenting, I was thinking way back to my material science days and wondering how different something like tritium is to other kind of core materials to technoscientific life. So like silicon now is ubiquitous, but it also, you don't find silicon in the ground like you find it in your computer, or lithium oxides or things like that aren't born in kind of nuclearity. And it seems like part of the story you're trying to tell is about like how certain groups of people are trying to make tritium a non-nuclear thing, or nuclear in a different way, so that it'll have all these benefits. And I'm just curious about the benefit of looking at other kind of core materials through the framework that you're using that either reinforce or kind of challenge the nuclear narrative, if that makes any sense.
Yeah, I'm not sure exactly how to get at that, but so what I would think too. So something else to kind of contextualize tritium, it remains exotic because of its sort of rarity, difficulty to produce, and difficult to hold on to. So, and I kind of hesitate to make this comparison because it's scientifically a little off, but I think conceptually it makes a certain sense. I sometimes think about tritium along those same lines as like neutrinos, right? Neutrinos are these very fast-moving, small particles that don't interact much with the things around them, and so anytime they're emitted, they're almost impossible to shield. It's impossible, and so if you're able to track them, whatever, you can determine. You know, so they got some people here at Virginia Tech doing some amazing things with neutrino detectors, right? Tritium is kind of slippery like that. It will, as hydrogen, as the lightest atom in the universe, it gets out of almost every system it's in. So it has this kind of like, you can contain it, you can purify it, you can keep hold of it, but it's sort of like, it goes beyond, it naturally goes beyond its boundaries almost in any environment, and sometimes very, you know, there was an infamous situation in Oak Ridge National Labs where they had a canister of tritium, they moved it across to a different building and then measured it, and there was like several grams of tritium had just disappeared somehow, and they're like, and this was a special built thing to keep it in there. So it's kind of a weird, it crosses boundaries very easily. And so in some ways it has this very, very weakly radioactive, but it is a weakly radioactive particle, beta particle comes off, but it's considered highly radioactive because it has a short half-life, and so it will tend to produce these reactions more frequently. But there's also this weird thing, it doesn't, and this is something I'm trying to figure out because it's used often in sort of rhetoric and cases against nuclear technology and nuclear energy as this risk and danger, and it's kind of aligned with all these other longer-lived radionuclides that are going to be around for thousands of years. But tritium is one of the ones that won't be around for thousands. Like, we literally just blew thousands of bombs off in the air and created tritium all over the planet, and we stopped doing that, and it's about back to normal with respect to tritium, right? This is a human scale problem. This could happen in a human life, right? This is not 1,000 years and barrel in the ground. So it's a weird fit for the nuclear conversation. I don't think people know what to do with it. Its risks and also its use cases, like, is this a byproduct? Is it special? Is this a fuel material that we can use? Does that help?
That helped a lot. Yeah.
Okay.
That's a good framing.
Oliver, do we have more questions on Zoom?
Not right now.
Okay, cool, thank you.
Okay.
Yeah.
Yep. Thank you for the beautiful presentation of your seminar talk. I want to follow on Monami's question about, but not on the co-production, but more on the historiography of your research, because you kind of like gave us the history of trillions and different stage of trillions and different stage of nuclearity. So I kind of like want to know more about how you position your research with among other previous study on nuclear weapons, history of nuclear weapons, or history of nuclear energy industries, and how you study on the different stage and different materiality or different nuclearities of trillions can benefit their understanding of trillions, can benefit the history of nuclear weapons or nuclear energy industries.
Yeah.
Very nice.
Excellent question. So there is no shortage of histories on nuclear weapons, and very formal, informal. There are that are internal histories written by scientists that have been declassified years later. Some that were released publicly. There's no shortage, but in all of those, tritium is really is a supporting character in all of them. There's very few documents that, other than highly technical documents, that feature tritium as a story, as this material being this sort of critical connection. So I didn't feel like I wasn't doing a kind of a primary history I really was surveying all this literature that exists and putting together this story that's already there, right? And so I relied on a lot of research and scholarship. It's hard to discover new nuclear weapons history stuff unless you file FOIA requests and things like that. But you can, there's so much out there, you can make a few connections and tease out a few examples that haven't been highlighted much, that haven't been used a lot, and connect them, put them in conversation. And that's what I did in my dissertation. And so yeah, I guess that's how I kind of saw my work in context of histories, right? I felt I was kind of like standing on the shoulders of giants, mini giants, and trying to help them see things that were already there, right?
That's nice, Taylor. I like that.
Hey, old friend. How are you? Congratulations. Good talk. So I have a question for you, and it is both an accusation and a question because we are old friends. In your talk, I kept hearing you say, tritium has like relatively no adverse health effects, right? So first, I'm wondering if you are complicit in constructing the no adverse health effects. And second, I want you to talk about that construction and how it relates to like sort of the sense of tritium as exotic and slippery and uncontainable.
Excellent question. I love it. So, yes, am I complicit? Yeah, I mean, to some degree. I'm doing my best. I'm making a good faith effort to assess what I consider to be risks worth worrying about and risks that we may need to think more and spend some more time on. What I want to emphasize that predominantly, even very staunch anti-nuclear activists that are experts in their own right will admit that very, very low levels of tritium are really hard to kind of quantify and hard to, yeah. So we're not really talking about that. What we're talking about, maybe if it gets concentrated, maybe these things that could happen and that do and have. I mean, in Arjun, in Makhijani's book, he uses the example of the lack of regulation for drinking well water for people that live near nuclear sites. So they don't follow an EPA regulation in the same way that our normal drinking water does. And in just a couple cases, he was like, well, there's this possibility, this possibility. They found one case where there was a little over 1,000 picocuries per liter in this well near a nuclear site, which is 1/20th of the US drinking water limit. And the drinking water limit, and I stress this in my dissertation, and I think it's really difficult to say this because the drinking water limit, whether you're in the US or wherever you are, the US has one of the most conservative. It's the lowest. Everyone else is like some, 1,000, 100,000 picocuries or something. It's huge. But I mean, these picocuries aren't huge anyway, so they're very small. So yeah. So in any event, so it's not that values below this are safe and values above that are unsafe. It's that, hey, this is additional radioactivity that we're adding to our environment, that we are exposing ourselves and our society to, and we need to be mindful and track it and keep an assessment of it so that when any epidemiological things emerge from that, we can trace it. And that's what's been the hardest thing to trace with radioactive damage, is these epidemiological kind of manifestations that you can separate out from other risks. Makhijani's book, I think, has some problems, but I think is very good in really highlighting an uncharted territory and looking at issues that are really foregrounded by the Treaty on the Prohibition for Nuclear Weapons and some of the recent successes by the ban treaty groups that are trying to forefront damage from testing, damage from nuclear weapons use to people and society. So, yeah, is that good? Okay.
I'm going to have Judman ask a question, and then I'm coming to you on Zoom, Daniel.
Hi, Taylor. Thank you so much for your talk. Something that I was looking forward to. So I really like the word in your title, ambivalence. So my question actually stems from this story that I read that the use of Patriot missile battery system for the first time in the Gulf War. So there were like scientific communities who were like, are in the controversy about the stories about efficacies of the missile batteries. So in the context of your topic, I'm like kind of interested to know what's going on in the scientific communities, like in terms of controversies and controversies about this uniqueness of this material, tritium, when they are developing weapons or any other kinds of things using this particular material.
Yeah, different things at different times. One example that comes to mind that Kalinowski uses as an example in his text. He did a lot of his research throughout the 90s. He'd been working on this issue for a long time, and he'd talked to lots of different people about it. And he recalls an anecdote where he was at a fusion energy conference, a fusion technology conference, talking to some experts that are physicists working on these problems, trying to figure out these complex things. He asked some questions about nuclear weapons. And they're like, what do you mean? And several people at this conference on tritium, on fusion and things, did not have any idea that tritium was used in nuclear weapons. And so in certain contexts, maybe it's lesser now, but at least in the 90s, and when he sort of recounts this, like, there are groups of people that are kind of insulated from this, and they're kind of self-insulating in a way. Yeah, and so the controversies, like for the radiological risks, I've got another kind of longer-winded example, but it would take way too much to contextualize right now, but I'll tell you afterwards, but it has to do with the Fukushima Daiichi releases and some of the controversies around that. It's an ongoing conundrum, and very, yeah. I'll stop there, but yeah.
We're going to Daniel in 1 second, but Kristen Koopman asked a wonderful question online that I know will warm your heart, Taylor, about the role of the TVA in all this. So keep it brief, please. I know you could probably go on for like 3 hours right now, but can you give a bit more historical picture of the role of the TVA in your story?
Yes. The Tennessee Valley Authority is the largest, public utility. No, sorry. Sorry, no. So yeah, TVA has a unique position in this, in that its original charter has national defense built into it. So when it was selected to be the site for that was part of the justification for its selection. It was selected. TVA applied. They were requested to be applied. They were the only plant to the only company to apply for that privilege. But yeah, so tritium is produced at Watts Bar since 2003, and they take those out and send them to the Savannah River site and extract it for nuclear weapons. And it's interesting. Several news reports. They're becoming a little more like. PR folks from Watts Bar are more open to talking about it, and in the last couple of years, they've said, "Hey, local people love the fact that we're supporting our national security here, and we've got a great community, and this is what they're doing. It's a very practical thing. It's economic, and it's not that nobody's trying to obfuscate anything. It's just this is what we're doing."
Nice. Going to you, Daniel.
Okay, great. Thanks, Taylor. This is really exciting. And I'm really delighted to see how this work is coming along. Can't wait to read it. One thing that I thought was really great and came out so clearly in your talk is that relationship of the materiality of tritium to the way that it's handled as a social process. You know, the way, for instance, how it's because of its short half-life, if you have a nuclear arsenal, just to maintain it, you have to keep it supplied with new tritium because it's losing it's decaying so quickly. But in your use of nuclearity and using Hecht's ideas, for me, that really raises the comparison to the Hecht's focus on uranium, and as sort of emblematic of nuclearity, a component and a necessary component of nuclear weapons that has completely different characteristics. It's focus of a global trade. It's a natural resource. It is, I don't know if this is true of tritium. She's very interested in how there's this tension between treating it as a commodity and treating it as something that has to be controlled and as a danger, as the sort of exceptionalism of uranium. What do you make of the comparison of tritium and uranium, these two really different things that are both necessary components of nuclearity, for what you're able to add to this whole concept, this whole conceptual framework that Hecht develops on nuclearity?
Yeah, excellent question. One of the interesting differences, and I think that I found compelling that drew me to the nuclearity concept and theory and framing, is that so I slightly riff on Hecht because she, in her text, she specifically talks about uranium not being born nuclear, right? It's this commodity, it's a metal, right? And people have been mining metal, and they'll mine gold and throw out the uranium in the tailings, and this has been going on for a long time. Or they might use the uranium for something, and it didn't matter. The radioactive properties were irrelevant, right? And so there is this sort of kind of tension, as material tension, as kind of defining it, assigning nuclearity to it, as opposed to sort of emerging, sort of fully formed from, Zeus's brow or whatever. So then that's sort of like what I saw with tritium, it being born nuclear, in the sense that it was it kind of already sort of christened in this domain, and it became this. Yeah, but it's also very, very directable, and I think in ways that a vast uranium supply chain, mining infrastructure that dealt with a lot of different governments and different organizations, and even down to the miner. Like, you don't have, tritium miners, right? You've got nuclear power plant operators at Watts Bar that are doing the same job they would be doing. Just a little bit more. They're doing a few extra tasks. That the additional dose and additional thing is very well quantified in their licensing amendments in a fascinating detail. But it's part of this job. It's part of this producing electricity, and this process is already contained within a defined nuclear space. But it's not a military space, right? So one distinction that you have with the tritium production at Watts Bar that really gives it this exceptional quality is that DOE personnel are there, and on site when tritium, the rods, the TP bars, the tritium producing burnable absorber rods are used or moved around or anything, DOE personnel are on site. And they're considered to be visually unclassified, so people can look at them without having to hide their eyes. People can see them, but they can't do any type of analysis. They're not allowed to do, you know, any type of penetrating analysis of the material, right? Even though there's fairly robust diagrams available of what these mostly are like. Just the specific exact constructions are closely guarded classified secrets still in this civilian space. So that's an extra layer that kind of gets added on with tritium, that uranium doesn't slip into that typically until it goes above a certain enrichment, right? And then you get these sort of magical numbers, and you're like, talking about Iran and talking about all these different contexts, and you say, okay, this is dangerous uranium, this is problematic. Tritium's always already there. If you have it purified, it's like, oh, you can use it for a watch face, or we could make a thermonuclear bomb, right? We can put these things together, and tritium is very flexible in that way, and so it's kind of a weird, hard to define, unique material, and that's why this ambivalence, I think, exists.
Thank you.
Thank you.
You are a scientific realist?
Yeah.
Because in this room, that's a very interesting position to be in.
I'm not gonna take the microphone.
I don't want to.
You want me to unpack that for you?
Yes, please.
Well, yeah, I kept thinking about, Daniel brought it up as your materialism. I mean, you really do focus in a very kind of realist way about what this material is, what its characteristics are, and then that's involved in your reasoning about the whole thing, right?
Yes, and I think I'm as much a scientific realist as Hecht is, I think, in her nuclearity constructions. And she assigns a stark realism to the materials and their potential effects, but allows some broader flexibility for the interpretation, the sort of contextualization of that, right? And it's just like, like whether or not a nuclear power plant worker gets exposed to 10 millirems of radiation while they're working in a day, or a pilot in an airplane gets exposed to 10 millirems of radiation flying across the Atlantic or whatever. So these two things are happening, right? But they're happening in very different contexts, and one is a rad worker taking dose in a certain way that's measured and controlled, but both functionally would produce the same type of potential damage to your DNA or whatever potential lies in a stochastic way over time. It could accumulate, blah, 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 right? There is this thing, right? So there is tritium inside the canisters, right? Yeah.
No, I think that covers it, although we could tell a story where the tritium isn't in the canisters.
That's right. We could.
I was just thinking about this. This might be kind of out there, but with Gabriel Hecht's nuclear exceptionalism and nuclearity, there's a very strong racialized component to it because of where uranium ore is found and all of those things. And in this case, with something being born nuclear, and this is kind of out there, so sorry about that, but there is a privilege that tritium has, if you want to use it in those kinds of racialized terms, that it does all, it's a flexible, it's like, what was that book called, science fiction book called Ubik? Sort of, this kind of, I forget. Philip K. Dick wrote it.
Yeah,
he wrote,
Ubik, yeah.
Ubik. And so this kind of material that's now being, peddled to us as sort of like going to save us in our climate change and everything with fusion, things that uranium cannot do.
Yeah.
And so there is some sort of racialization, and I'm maybe that's kind of out there, but that there is this sort of privileged position, at least with respect to uranium, that tritium has, based on everything you've said about it.
Yes, and that's very fascinating, because there is this sort of abstract quality to tritium as a material. It's a colorless gas, difficult to measure, but it does have this very kind of laboratory life, like purified, sanitized, separate from, the blood and sweat of labor, of mining, of these sort of real world contexts. Even though it's connected, I think, to it through lithium. And so that is the kind of the sort of unspoken kind of co-conspirator behind all this is lithium's role in this. And I think there may be I should do a supplement later on and sort of tie in how lithium supports all this. But that is, I think you would probably map that through lithium to connect it to these real world mining things. But people talk about lithium, huge for batteries and all these massive uses, and the quantities for this are very discrete, very minute, but precisely and enriched in a certain way and very scientized. Yeah.
Thanks. This is great. And this is kind of a slippery question for a slippery substance, I think. But it kind of connects to Monami's. I'm thinking about fusion. I mean, you haven't talked very much about fusion. And there's this sense in which fusion is itself a slippery substance, not substance, but process. It's immaterial in a way that I think that traditional nuclear power is not, which is contained by metal and concrete, and fusion is contained by magnetism and hope. And so I'm just wondering if you have. I was just wondering if you had thoughts about the kind of cultural. So this is kind of going back to the nuclearity and the shifts in nuclearity and the ways in which, as tritium increasingly gets connected to the kind of fusion economy, that its own immateriality and the kind of contrast with the uranium conception of nuclearity shifts our understanding of what nuclear is, of what we're doing, and what the kind of political economy and global politics around the nuclear become. So I'm not sure where the question is in there, but yeah. Thanks.
So yeah, I think that there is, and I think I would situate this as part of the sort of fusion hype train. So yeah, there is some hype around fusion, and it does rely on a lot of these sort of narratives that separate it from fission, that make it distinct, and sort of talk about this is in the same utopian dulcet tones that fission once was, right? And then grim reality showed us that it's harder than that, and we got trade-offs. And so maybe one day we'll have technologies without trade-offs, and then we'll no longer have STS to save us from anything. So right, I think there is some of that, but I look at it in a very practical way from my standpoint, my research, and from looking, and you may have caught on to this from some of my recent fusion piece I published last year. If we're going to keep experimenting on this, if we're going to keep progressing toward this direction, let's do so in kind of a mindful way, and let's not let one camp define what this technology means for the rest of us, right? And so tritium is the heart of this. Tritium is the heart of nuclear weapons. Tritium is the heart of a potential fusion economy. Are we going to let this sort of invent itself and kind of go, let the market decide or whatever? Or are we going to be very kind of looking back at what we know from tritium history and where we are at now and say, if this happens, we need to kind of have control mechanisms and this robust, holistic understanding of what this material is, so that hype doesn't drive the definition of what fusion is or can be or even should be, right? So I don't know if that gets you there.
I want to just note that we are not able to get to a wonderful question from Rich about the Canadian tritium scene. That would have been extremely juicy, I know.
Yes.
But Taylor, I want to thank you so much for your talk, which was as good as we all knew it would be. And congratulations, and yes, good work.
Thank you.